Good morning, everyone. Myself Subhranshu Sekhar Jena, and I am from Baleshwar, Odisha. So today, for this lecture, I am going to discuss about the zero order kinetics. Okay, it's from the chapter of chemical kinetics. So we'll be discussing in the chapter. I will write the topic name here. It is from chemical kinetics. To be more specific, I'll be discussing on the I'll be discussing zero order reaction. Okay. So in these two lines, there are two terms that we should be clear about. So first term is your kinetics. So I'll briefly explain the term kinetics. Okay. If someone hears this term kinetics, what the person should understand about this term. So now let us imagine a classroom is there. Okay. In the classroom there are two students. I am imagining a student, student A, student B. Now if I am saying student A have to share one pen, the A have one pen and it wants to give to B. There are how many ways that the pen can be given to B by A? So many ways are there. Someone will say, oh, by this way we can go. Someone will say, no, this way, this way, this way, this way, if this way. I have drawn here specifically 1, 2, 3, 4, 5 ways. 5 ways. So among these 5 ways, which path? 5 ways means 5 paths. So out of these 5 paths, which path should be followed? That actually decides kinetics. That decide which path we should take, and that decision was made with the help of kinetics. So specifically, I can say kinetics decides the path that should be followed. Okay. So I have now you are clear with the term kinetics. Now let us move on to what is the order of the reaction. I will erase these things. Fine. Now I will be discussing what is the order of reaction. Order of reaction. Order of reaction is the summation of powers in the rate law expression. The rate law expression. Now what is rate law expression and how to write that? So rate law expression specifically depends on the concentration of reactant. Now let us imagine a reaction is going on, A giving rise to product. Okay. So now the rate law, and it's a single step reaction, and all the single step reaction are known as elementary reaction in the chapter of chemical kinetics. So the rate law for this can be written as rate proportional to concentration of A with the power, let's say alpha. Here alpha corresponds to order of the reaction. Now if I have to remove that proportionality constant, it will become A alpha. Okay. Now if the alpha is equal to 0, then it will become zero order reaction. 1, it will become first order reaction. If alpha becomes 2, it will become second order reaction, and so on so on. So now we got some basic idea about what is zero order reaction. Now we will be dealing with the kinetics of zero order reaction. So we move this, all these things. Okay. Kinetics of zero order reaction. We know that okay, we'll imagine a general reaction. Let's say a zero order reaction that going to product P. This is a general zero order reaction. Okay. Now here you can see that A is going for decomposition, because since A is forming product, there will be decrease of amount of the reactant A. So I can say that there is decomposition of A is happening. Kinetics would define the differential rate law as minus of dA by dt, minus of dA by dt. So now this is also a rate, so this will become equal to K into concentration of A, and the power is generally, we know that the summation is defined as what we discussed that the power is the power actually corresponds to the order of the reaction. Now since it is the zero order reaction, here I can write that is minus dA of dt equal to K or 0, and any species with the power of A will become 1, so it will become minus dA by dt K. So now if I do this one, I'll do I'll take the dt on that side. Now it will become dA equal to K dt. Okay. Now I will integrate on the both sides. If I integrate it on both sides, what I will get dA, K is constant, so I will take it out. Now when T equal to 0, our concentration will be A naught. A naught corresponds to concentration. When T equal to some time T, the concentration of reactant will become concentration of A at time T. Okay. Now the integration of dA will become A, and AT, here also minus K T 0 T. Now putting the limits, we will be getting AT minus A naught equals to minus K into T minus 0 T minus 0. Okay. So I can write like that, AT minus of A naught equal to minus of KT, minus of KT. You can rearrange it to write A naught minus AT equals to KT. So what is this? This is the integrated rate law expression of zero order. Now there is a concept of half-life also for any order of reaction. So now I have to calculate half-life of zero order reaction. So what do you mean half-life? Half-life means, let's say initially no reaction is happening, so I can say the 100% of the reactant is still present. So the time at which 50% of the reactant is consumed, that time is known as half-life time. Okay. So the time 80% of the reactant is consumed is known as half-life time. Now what will be the expression for the zero order reaction? So expression for the zero order reaction, that we know that at time t, at t half time, the concentration of the reactant will become half 50% of the consumed. That means it will present 50% of the reactant. So I will rearrange that initial equation k t. Now at half-life time, a t becomes a naught by 2. It will become k into t subscript half. So on rearranging this, I will getting t half becomes equal to a naught by 2k. So these are the things. So based on this, we will be discussing one numerical that will be helpful for this one to understand this. Remember one thing, only the zero order reaction is the only reaction that goes for 100% completion. Except the zero order reaction, no other reaction goes for 100% completion. Okay. So now I'll clear the things and will be discussing one numerical based on these two formulas. Okay. So I'll write the question first. Let's say A giving rise to product P, and it follows a zero order reaction. At 20 minutes, the half of the reactant is consumed. Okay. So calculate the time required for the 80% completion of the reactant if the initial concentration of reactant is 10 molar. Now what are the data we've been given? I'm writing for these things. So this is saying that T half 50% is completing in 20 minutes. That means I can write that T half will be equal to 20 minutes, and we are given by A naught as 10 mole per liter. Okay. Now it is asking what will be the become T 80%. Now using these two data, I can calculate K. How? The formula will become T half equal to A naught by 2k. Now K will become A is 10 and is T half is 20 minutes. So we are getting 1 by 4. Now with the rate constant. Now it is saying calculate the. Now what is saying? Calculate T 80%. See, T 80% means 80% has been reacted, and we are left with 20% left. So now if we write the equation, it will become KT, whereas we need to calculate T. So A naught is your 10 and T is 20% left. 20% left means we can write this one. 0.2 of n. 0.2 of n. One minute. This is a naught minus. This will become 0.2 a naught. Equals to k. We got 1 by 4 into t. 1 by 4 t. Now it will become 0.8 a naught. It will become 0.8 a naught. 1 by 4 into t. Now a naught is your 10. 1 by 4 into t. So t becomes 32 minutes. So this is the traditional way to solve the numerical for zero reaction. In exam, let's say we cannot solve these long processes, so we need to go fast. So we'll try a different way also. Since I mentioned since I mentioned that zero order reaction only the zero order reaction goes for 100% completion. So unitary method is valid for the zero order reaction. Unitary method. That means it is saying that 50% is completing in 20 minutes. 50% is completing in 20 minutes. Now for 1% completion it will become 20 by 50 minutes. 20 by 50 minutes. Okay. For 80% we need to calculate the minute. 1 minute, just a minute. So for 80% will become 20 by 50 into 80 into 80. So cancel out. So 5 becomes 4. So become 32 minutes. So just 3 lines the question is solved. 32 minutes. So this is the trick to solve zero order reaction with the unitary method within the fraction of second. You can see that within the second we have solved this out. Okay. So thank you for today. Okay, thank you.